So, good afternoon, everyone. Welcome to the week 8 of live sessions on finite element method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, in the last week, that's the week number 7, we were studying about how we deduce the formulation for the element equations of a beam element. In last class, I completed that module wherein we saw the complete element equations for a beam element, where like this, yeah. Here is the complete stiffness matrix of a beam element where it is K is equal to stiffness matrix is equal to K E by L. E is modulus of elasticity, I moment of inertia, L length of beam element. Then this matrix 12, 6L minus 12L minus 6L, and it's symmetric from this part. Okay. And we have other two vectors as well. One is the nodal force vector that includes the distributed load that may be present on our beam element. It is given as QL by 2, QL square by 2. This is force, this is moment, this is force, this is moment. Okay. Then we have other vector as well. That is the applied forces or moments that may be present at the nodes, that is F1, M1, F2, M2. And we have another one more vector that we already know is the displacement vectors, or the vector of degrees of freedom. We have two degrees of freedom at each node. I told you in the last class, one is 2 degrees of freedom at each node. One is the vertical displacement and one is the rotation or the slope at that point. And at the since we are having two noded element, so we have 4 degrees of freedom in total. Okay. So our stiffness matrix also comes of order 4 cross 4. So using the same formulation, today we will be solving some numerical examples on this, and then we will move forward to the frames, wherein we will be having one more degree of freedom, that is the axial force, and we will see if time allows us to solve one more problem on frames as well. So let us start today's lecture with a basic problem from the beams. So problem first for today's session will be, okay, so we are given a beam which is having following supports. We will be solving the complex systems here only, because we have already seen in structural analysis how to solve the determinate structures. So here we will see indeterminate only. So it is supported at ends like by these. Okay, then it is having two more intermediate supports at equal spans, one more intermediate support here and one more intermediate support here. Okay, and these all are equal spans of length 400. Okay, 400 mm, 400 mm, 400 mm. Okay, then what else is there? We a point load acts in the middle span, whose value is given as, it is 8 kilonewton, and actually it acts at the middle point of the mid span. So this has to be 200 mm. Okay, so what we need and additional information that is given is modulus of elasticity of the beam is 200 GPa, and moment of inertia of the cross section, since it is a prismatic beam, so it is having a uniform moment of inertia, a uniform cross section with a moment of inertia 10 to the power 4 mm power 4. Okay, this information is given to us. What we are required to find, we are required to find the deflections, moments, and shears in the continuous beam. We have to find deflections, moments, and shears. Okay, these things we have to find. So first of all, looking at the configuration of the beam, how beam is present, we can easily see there is a symmetry present in the beam. So we can analyze half part of the beam, and then the same half part will be the replica of that part. So we need not unnecessarily compute the reaction forces at all the four supports. Instead, we can see the symmetry in this beam, and then we can divide it into two equal parts and analyze only one part. So looking at the symmetry, we can see that the line of the symmetry is like this, like this. Okay, we can divide this beam into this part and this part only, and we can analyze one of the parts. So if I can take this beam from here, if I take this beam from here, this part, and take only half part of it up to this thing, and analyze only this part. But one thing we have to make sure is we have to make the continuity from where we have taken it. So if we see at this point only, if we see at this point, like this point, so here deflection is allowed. So deflection is allowed, but this rotations are restrained. So rotations are, so only then when these two conditions are met, the continuity in this beam is maintained like this. Okay. So for that, we have to give the support conditions accordingly. So first is like this. So this, this, and this will make sure the vertical displacement is present there, but this support condition will make sure no rotation is there. So displacement will be there like this, displacement will be there, but rotation will not be there. Okay, I'm just showing for you people. And since we have taken the only half part, this was 8 kilonewton load, I will take only 4 kilonewton load here. So 4 kilonewton load will be acting exactly at this point. Okay. So what I will do is that since these are two equal parts, this is of length 400 mm and above one is 200 mm. So I will take this one as element 1 and this 2 as element 2, because since there is one intermediate support in between, I can take this one as element 1 and this 2 as element 2, and then I will analyze, write the equations for the individual elements and combine and assemble the equations to get the global systems. In the global system, put the boundary conditions. After putting the boundary conditions, reducing the system. After reducing the system, computing the displacements and rotations. So what I decided is that I can take this as element 1, this as element 2. Okay. So after this, how my configuration looks like, it is like this. Okay, this, and this. Okay, sorry, this should not be square. Okay, this is element 1, this is element 2, and the nodes will be, so there will be, like, what will be the degrees of freedom? There will be vertical displacement v1 here, vertical displacement v2 here, and vertical displacement v3 here, because at each node there are 2 degrees of freedom. So what will be the other degrees of freedom at each node? It will be the rotations, that is here it will be theta 1, it will be theta 2, and it will be theta 3. Okay, so starting from the element first. Okay, so if you see the element first, this one element, its length is 400 mm. Okay, its length is 400 mm, and E and I are given constant for both elements. So writing the equation for element first, so element 1. What are the conditions given? We have given as E is given as 200 kilonewton per mm square, L is 400 mm, and I is 10 to the power 5 mm power 4. Okay, then what will be the equation system? So we have to use this equation system. Okay, so week 7 it was given, we have to use this equation system. Okay, first this kd times k times d is equal to rq plus rf. K is this, d is v1 theta 1 v2 theta 2, rq. Rq will not be applicable there as there is no distributed load. There will be rf only. Okay, because there are only applied loads, point loads only. So first we will write the stiffness matrix quickly. First let me write the stiffness matrix. So for a beam element K is given as, you have to remember that K is given as, we have first KD is equal to uh, RQ plus RF. Okay, all are matrices, so we have to bold them. Okay, where K stiffness matrix, that is the most important component, that is given by EI, that is given as EI by L, EI by L, and then it is 12 6L minus 12 6L. That is that is 12 6L minus 12 minus 6L, and then other contents are 4L 4L 12L 4L 4L 12L 4L. I think it's 4L square. 4L square 4L square. This is minus 6L minus 6L minus 6L minus 6L. Okay, this is symmetric from this. Okay, so if you use this equation, then we have we have to put E value 200 into 10 to the power 3 Newton mm square. We will keep mm square like that. I is 10 to the power 5 mm power 4, and we have L as 400 mm. We incorporate all these values, no, here all these values into this equation, and for each L is 400 mm. And then put the different values of 12 6 into 400 minus 12 minus 6 into 400. So I just show this for your purpose, showing purpose only. Okay, so this is our, just like this, for our information only. Okay, okay, 400 6 into 400, and then put all these values here, 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 here. It is symmetric, and it is equal to RQ plus RF. First it is multiplied by V1 theta 1. Okay, sorry. This is multiplied by, look at the degrees of freedom for first element. This is V1 theta 1 V2 theta 2. So put those one, V1 theta 1 V2 theta 2. Okay, V2 theta 2, that is equal to 0 0 0 0 0 0 0 0. Okay, like this. And then element 2, for element, if I solve this system of equations, what I will get is this one, this matrix, closed matrix. Okay, 3.75 750 minus 3.75 750. I will get 210 to the power 5 minus 750 10 to the power, I will get 10 to the power 5 minus 750. I will get one more thing, 3.75. This is minus 750 minus 750 here. This is 2 into 10 to the power 5. It's 1 into 10 to the power 5. This is minus 750 minus 3.75, and this is 750. And if you multiply it with by V1 theta, this is minus Hello, hello, are you able to hear me? Hello,
Hello, Danish. Now
actually,
you are audible. I think the
yeah,
network
actually
went off.
there was a network problem. Sorry. Okay.
Yeah, yeah, not a problem. Now I'm
So,
able to hear.
so
Yeah.
are you able to hear me?
Yes, yes, I'm able to.
So I was telling about element one. That was visible to you people, huh? Element one.
Yes, till this point it was there
Okay,
when you
till
were
this point,
listening.
this
Yeah, yeah,
element one, huh?
yeah. Right, right.
Okay, okay. Thank you, thank you. Now the network is back. I will continue. Okay, thank you.
Yeah, not a problem.
Okay. So now we have to see this for element two same equations. We have to write for element two how we can do that. Let me do that. For element two is again same. For element two is again same. E is equal to 200 kilonewton per mm square, and but here the length is changed. L is 200 mm and I is equal to 10 to the power 5 mm power 4. So if you put the values in the element equations again, this element equation, okay, you will get a matrix like this. It is 33,000 minus 33,000, 4 into 10 to the power 5 minus 3,000, 2 into 10 to the power 5, then 30 minus 3,000, 4 into 10 to the power 5. V2 theta 2, V3 theta 3. So these are element 2, V3 theta 3. Its nodal degrees of freedom is equal to. Now at node 1 again. Node 1 again, there are no forces, but at node 2, there is one force like this 4 kilonewton. Okay, we have to include that, and that too is in downward direction. Our upward direction is positive, downward direction is negative. So this is minus 4 kilonewton. Okay, hope you are following this. So we will be having 0 0 v2 theta 2, but v3 is minus 4. This is 0 again, like this. Okay, then continuing the same thing, what we have, we will assemble all these equations, element 1 and element 2. So element 1 and element 2 equations will be assembled like assembling the equations. Element equations, global equations are, okay, global equations will be looking like something this. So we have to take this, okay, copy this, and then there will be two more rows. Okay, two more rows of this. It will shift two rows here, two rows there. Okay, so it will be, sorry, it will be same thing like this. Since we have done the numbering continuously, so element to equation like this will be overlapping like this. Okay, there will be two more elements, so there will be only one difference here like this, and other node elements will be, so we have to change only these four values. Okay, so these four values will be these two, this will be 6,000, This will be 6 into 10 to the power 5, 10 to the power 5. This will be 2250. This will be 33.75. This will be 2250. And all the other entries will be 0000. And this will be minus 30 here again. This will be minus 3000. This will be 3000. This will be 2 into 10 to the power 5. Okay, this will be minus 3000 again here. And other these 4 will be 0000. Okay, 0000. Then we have the nodal degrees of freedom global system as it will be we have v1 theta 1 v1 theta 1 v2 theta 2 v3 theta 3. These are the total global system. And global force system is only minus 4 is there at one place. So we need to shift it little bit like this. Little bit okay. So the force is 0 0 0 0. Then there is minus 4 once, only once time. Then is 0 again. Okay, this one. Then what are the boundary conditions? We can see that the boundary conditions, that is v1 v2 here, v1 is here, v2 is here, both are 0 because these are supports there, so vertical displacements will be 0. v1 v2 will be 0. Theta 1 theta 2 will not be 0, and also theta 3 will be 0 because rotation is not allowed. So we will incorporate those three boundary conditions. So boundary conditions for our problem will be v v1 equal to v2 equal to 0, and we have one more boundary condition, that is theta 3 is equal to 0. But I told you where there is 0 displacement or rotation, obviously there will be the reaction coming on at that point. And for displacement, 0 displacement, there will be reaction, and for 0 rotation there will be reaction moment. Okay, so if we will do that thing here, we will have to put this to be equal to 0, this to be equal to 0, and theta 3 equal to 0. I told you what is the trick for that. Where there is 0, you have to delete that row, this row you have to delete, and this column you have to delete. Then again we have third row, you have to delete third row. Okay, you have to delete third column. Okay, then we have 1 to third, for sixth you have to delete sixth row, you have to delete sixth column. Then we are left with only these values, very small values, this. The reduction in the matrix will be so huge that we'll be left with only three unknowns and their respective values. It will be 2 into 10 to the power 5, then again it will be 1 into 10 to the power 5, then it will be 0, it will be 1 into 10 to the power 5, then it will be 6 into 10 to the power 5, this will be minus 3000, this will be 0, this will be minus 3000, this will be 30, and we are left with degrees of freedom only theta 1, theta 3, v3. Okay, so theta 1, theta 2, sorry, theta 1, theta 2, we are left with theta 1, theta 2, sorry, this is theta 2, theta 1, theta 2, theta 3, v3. This is theta 2 and V3, which is equal to 0, 0, minus 4, 0, 0, minus 4, okay. So when we solve this system of equations, we have three equations. We have three equations, one, two, and three equations. We have three unknowns. We will easily get our three values as theta 1 to be equal to 0.0008 radians, and we will get our theta 2 to be equal to negative of 0.0016 radians, and we will get our vertical displacement V3 to be equal to minus 0.293 mm. Okay, these are the required values. So this is only the half question. We have to find other things as well now. So we found the displacements, unknown displacements and rotations that were required in our structure. Okay, then moving forward, our displacement will be. So now we have to see the displacement equations in the individual elements. So for element 1, okay, for element 1 we have to see what are the things given. Element length L is given as 400, okay, and what we have the nodal solution D. What was D to be equal to, what we got, V1 is 0, we got theta 1 as 0.0008, okay, V1. V2 is again 0, we got theta 2 is minus 0.0016, okay. This is the nodal solution of this element. So we know that displacement is given as displacement in within the element V of S has the form of this 1 minus 3s square plus 2s cube. Another is L times S minus 2s square plus s cube, where s is the parameter that varies from 0 to 1 within the element. 3s square minus 2s cube, okay. L times minus s square plus s cube, okay, times the nodal parameter, this one, 0, 8 into 10 power minus 4, then 0, that is 16 into 10 power minus 4, that is minus times. If we solve this, we will get an equation for Vs in element 1 to be equal to 0.32s minus 0.32s cube, okay. This is for vertical displacement within element 1. And similarly for the moment, we have the equation moment m as bending moment. Bending moment ms within an element is given as E by L square, EI by L square times minus 6 plus 12s, 3 times minus 4 plus 6s, 6 minus 12s, and then 3 times minus 2 plus 6s, this, and this is their nodal 0, a 10 power minus 4, 0 minus 16, 10 power minus 4. When you solve this equation as well, you will get for moment equation to be equal to minus 240 s, okay. So at the, so this was our element first, okay. Element first, s was equal to 0 here, s was equal to 1 here, okay. S was equal to 1 here, okay. So we will get the moment here to be equal to m to be equal to 0 and moment to be equal to minus 240, okay, kilonewton mm here, okay. Similarly for shear force, you can directly write, you have to just integrate this once. That is shear force V of S to be equal to EI by L square. That will be equal to 1218 minus 12, 18, and it will be 0, 8 into 10 power minus 4. Then again 0, it will be 16 into 10 power minus 4, minus times. If you will see, shear force V of S comes out to be a constant quantity of G minus 0.6 kilonewton. Okay. For element 2, so for element 2, what are the nodal vector what we got? We already know we have a element length of 200 mm, and our nodal solution D for that one came out to be, if you look here, what was the D here? Here D was theta 1 was 0. For element 2, theta 2 will be theta 1, 0.0016 radian, but V2 is again equal to 0. V2 is again equal to 0, and V3 comes out to be is S, and theta 3 is equal to 0. So I will write down that nodal solution. Nodal solution is, sorry, 0 minus 16 into 10 to power minus 4. Another is minus 0.2933, and last rotation theta 3 is 0. Okay, nodal solution is 0. Similarly, what we do here for the displacement like this, bending moment here and shear, we will get all the three equations for displacement V of S to be equal to minus 0.32 S minus 0.24 S square plus 0.267 S cube, and moment we will get to be equal to M of S to be equal to minus 240 plus 800 S. Okay, so at S equal to 0, it is again minus 240. Okay, so and at S equals 1, it is equal to 560. Okay, shear force V of S we will get to be a constant shear force of 4.0 kilonewton. So and it is visible from the geometry of our structure as well. So here this is 4 kilonewton, here it will be all through this element up to this point 4 kilonewton. So like this, it is 4 kilonewton here acting, so it 4 kilonewton will be acting up to this point only. Okay, then there will be only 0.6 newton acting up to this point. Okay, we got all the things, so we can easily plot the deflected shape as well as other things as well. So if we see for the deflected shape, so for deflected shape we have to use V of S equations. Okay, V of S we have, this is cubic as well here, and this is here as well, this is cubic. Okay, so we will have two cubic parabolas like this. Okay, this is for displacement. Displacement, and for moment, how moment is changing, you have already seen that. So moment you have seen at the left hand, first it is 0, then up to the point it comes out to be 240, and then again it shoots up to 560, 560 here. Okay, this is 560 kilonewton mm, this is minus 240 kilonewton mm. Okay, you remember these values. And how shear force is changing, it's very simple. Shear force is changing in the first element, shear force is zero point 0.6 newton minus zero point 0.6 newton, it's 4 newton. So this is minus zero point 0.6 newton up to support, and then it shoots up to 4 newton. So this is 4 kilonewton minus 0 0.6 kilonewton. This is shear. And if you remember, this is the point here. This is the point where the support is present. Okay, sorry, I'm not showing this correctly. not showing this correctly. So actually, this here, moment, displacement. Okay, this is point here. Okay, so our beam was like this. Our beam was like this. So we were having one support here. We were having one support here, and we were having one vertical roller here, like you can imagine. So this completes our problem. Okay. So you can find individual solutions for each element now and draw the free body diagrams. Okay, that is not a big issue now. You can solve the similar problems like that. Number of complex problems. There will be the change in the section of the elements, or there will be the change in the section of the beam. So you can, wherever there is a discontinuity either in the material or the supports, you can change to the number of those number of elements. So it's very easy. So I think this was all in within the beams. I think the one more thing we are pending is plane frame element. So now we will be seeing the plane frame element. Okay, this is beams. In beams, you can solve n number of problems. Similar approach you have to do. First, you have to see the configuration of the beam, then select if there is symmetry present, decrease the degrees of the freedom if there is symmetry present. Or this, after the symmetry is present, you have to check or the number of elements you have to take. So for the current problem, we have to take only two number of elements because there were only one intermediate support. So if you have two intermediate supports, you have to divide it that into three number of elements problem. Then you have to write the element equation for each element, and for then each element you have to arrange that element equation into a global system, and that global system you have to put the boundary conditions, and after putting the boundary conditions we can get our desired displacements and rotations. Those displacements and rotations, when put back into individual element equations, we can get the equations for the vertical displacements. We can get the equations for the bending moments as well as the shear force. So that's very easy now. So actually, what happens in a plane frame element is that plane members in the plane frame are designed to resist the axial and bending deformations as well. So in first case, like if we had, so let me show you how we started. In first case, we saw only bar element in which we saw only axial forces are present, so they are deforming through axial deformations only. Okay, PP. So then it is deforming through axial deformations only. Then we saw beam elements. What we saw here is we saw there apart from this there is a bending deformation like this. There may be loads present transverse direction to the axis, so there will be bending deformation. Okay, so it is axial deformation. So we have bar element here. So we had 1 degree of freedom here at each node, and we had 2 degree of freedom at each node. Okay, so what we do is that if we combine these two things, like we have to combine this and this, if we combine these two things, so what it gives is our plane frame element. Because what frames have to do apart from resisting the bending, they have to resist the axial deformations as well. So for example, this is our plane frame element like this. So apart from bending, like at bending it will be having two deformations like this it is having 2 degrees of freedom from bending, we have one more deformation, that is actual actual deformation as well. Okay, so we have 3 degree of freedom each node. Okay, I hope you people are getting my point. So let's assume this is its x-axis, this is its y-axis, and these are the degrees of freedom: d1 here, d2 here, and d3 is the moment. Then d4 is this, d5 is this degree of freedom, and this is d6 degree of freedom, and L is the total length of the element. L is the total length of the element. Let's assume E a I constant. Okay, all these things to be constant. So what I represent, this represents the nodal degrees of freedom. Okay, so it has total 6 degrees of freedom, and at each node it has 3 degrees of freedom. This is node x1, this is node x2. Okay, so for example, if we see the same element, but what we see, the what will be the external forces that will be applied. So the external forces can be axial force like this in this direction, in fx1 direction, where we can have transverse shear fy1 on node 1, we can have moment m1. Okay, we can have moment m2 applied forces. Okay, m2 we can have axial force fx2, and we can have shear force fy2. Okay, 6 applied forces. So if this is x direction, this is y direction. Okay, now, okay, this is applied forces. So for example, it's also subjected to some uniformly distributed load q. Okay, so these are applied nodal forces, and udl. Okay, so we know that. So from our basics, we know that for axial deformations from the bar problem, you know that what for our bar problem we wrote the element equations. It is ea by l. You people should be knowing and remembering this equation by this time. 1 minus 1 minus 1 1, d1 d1, and I'm writing d4 because those are the only actual degrees of freedom. D1 and d4 are the actual degrees of freedom. D1 d4, and what are the actual forces present here? fx1 fx2, fx1 fx2. So you know it from the bar problem. Okay, from beam bending or for bending deformation. So for bending deformations, we know we have E I by L cube. We have the matrix that we studied earlier, just few minutes ago. 12, 6L minus 12 minus 6L. 4L square minus 6L, 2L square. Okay, 12 minus 6L, 4L square. Okay, this is like this. And what are the degrees of freedom that we have to use here? We have to use d2, we have to use d3, we have to use d5, d4 is already used, and we have to use d6. And what are the bending forces that are involved? That is shear force F. y1, moment m1, fy2. I hope you people are connecting this. This is very easy. M3. So what we have to do is that we have to combine these two things. We have to combine these two things into a one single system to give the element equation for our plane frame element. Okay. So uh, combining. So what I write combining above two systems for plane frame element. So when I combine above two systems for plane frame element, I will get a system of equation like this. This is A1, this is 0, this is again 0, this is minus A1, this is again 0, this is again 0. Okay. Then in the second way, I have to write 12A2, this is again 6LA2. Okay, this is 0 minus 12A2 and this is 6LA2. Okay, then here I have to write 4L square A2. This comes again to be 0 and this comes down to minus 6L A2 and this comes to be 2L square A2. Okay, then moving forward, this comes out to be A1 and this comes out to be 0 and this comes out to be 0 again. And then this comes out to be 12A2 and this comes out to be minus 6LA2. Okay, and this comes out to be 4L square. Sorry, this comes out to be 4L square A2. Okay, and why am I not writing these sided elements? Because this is symmetric. Okay, this is symmetric. Okay, this one. So the nodal degrees of freedom, I have to write all nodal degrees of freedom. Okay, D1 to D6. This will be D1, this will be D2, this will be D3, this will be D4, this will be D5, this will be D6. Okay, okay, this one. And what will be the nodal force vector? This will be Fx1, Fy1, M1, Fx2, Fy2, M2. Okay, this system. Okay, where I have used the constants a1 and a2, their values are a1 is equal to ea by l and a2 is equal to ei by l cube. This is from the bending and the axial deformations. Or we can write this to be collectively, this matrix collectively to be equal to k, and this matrix to be collectively equal to d. You remember these notations, and this matrix collectively to be equal to rl. Okay, so let me write for LL for local systems only. So we can write KL DL is equal to RL, because these are in local systems where the bar is not inclined, or the space plane member is not inclined to any inclination, because it can be inclined like that of a truss member. Okay, and there will be one more thing, RL can be other things and as well. So I think we will study that inclined plane member in the next class, as the time is already over. So thank you everyone for joining. You people can leave now. So this was actually plane frame element. plane frame element. Okay. Thank you, everyone.
Okay, thank you.